Hello everyone. Today we're going to talk about models for sequences. This includes recurrent neural networks, LSTMs, and some more. One thing you might not have considered is that fully connected neural networks have a predetermined input size. But now, what if you don't know the size of your input, or it comes in a symbol at a time, like a sequence, or communication? If someone is speaking, you don't know exactly how long they'll speak for. One of the interesting things is that there's no immediate way for a fixed size neural network to take into account this kind of information. This is actually the most basic function of recurrent neural networks. They can take in arbitrarily sized inputs and remember the hidden state of information. So if you could imagine that this is the instantiated network, it has a hidden state where it actually remembers because it's getting the previous hidden state. And so the information through this network is accumulating along with the iterations of operation. Of course, for this to happen, there are both feed forward and self loops in this kind of a neural network that feeds back the information into the hidden state. This is what causes them to be called recurrent networks. Recurrent networks have proven to be extremely good at natural language processing tasks like speech recognition, language understanding, machine translation, text generation, music generation, and much more. The basic idea is that if you have spoken language, such as this sentence, you can keep accumulating information until the speaker stops. Now you have accumulated state, or a representation of this entire sequence of information here, and now you can perform your output, which could be a translation task, for example, from German to English. Sequence-oriented tasks can have many different structures. So, of course, there could be sequence-oriented tasks that spit out a symbol every time they see one, or spit out an element every time they see one. Or you could see one input, like an image, and then you might want to generate a sequence of outputs, like a sentence describing that image or a caption. Of course, you can have many to one. You can classify a sentence. You can wait till you read in the entire sentence and then classify its sentiment. This is called sentiment analysis. Is this mainly positive or is this mainly negative, etc. You can have many to many, which we just saw in the translation example. And we can have many to many that's concurrent. But what all of these have in common is that there is some kind of sequence of information that's coming in that the network is remembering, so to speak. Of course, backpropagations can still work here, but what happens when we do that is we really unroll this into many timestamps, and we perform backpropagation through all of these as if they were a multi-layered neural network. And that's called backpropagation through time. But the simple model that I showed, which is called a recurrent neural network, does have some drawbacks. One of its drawbacks is that it's not very good at handling long-term dependencies. In other words, it forgets information which is too far in the distant past. It's a little bit of a vanishing gradient problem because it's too many neural network layers to backpropagate through. We had seen these problems in fully connected networks, and we'd seen that one of the solutions was skip connections. So the idea is you want some way of forwarding the information through the iterations like we had through the layers. Here is where LSTMs were one of the most famous attempts to do this. LSTMs have these recurrent units that are somewhat more complex than a normal recurrent neural network. Just to get you used to this idea, the main component they have is a running cell state to which you add and subtract information. So the cell state could be carrying information from the distant past to the current iteration. The cell state is something that the network adds and takes away information from via gates. Gates are normally sigmoidal layers that control how much information from the previous state or the input it lets through to this running state. In particular, LSTMs have a forget gate that says how much information from the previous hidden state should be forgotten, and they create a new hidden state by looking at the current layer of the neural network and the computations performed there that take into account the previous state and the current input, and the forget gate. So you're forgetting some of the previous state and you're adding new state in. And that's how this running state works in an LSTM. And finally, it does have an output that you can output at each stage that's also controlled by this kind of a sigmoidal function, which takes into account the running state as well as information from the ordinary hidden state and the input. LSTMs can do very similar things to recurrent neural networks. So they can do machine translation, they can do question answering, for example, and this is again this sequence to sequence model where you're taking in a whole sequence of input and then you're representing an intermediate state from which a sequential output can come about. But in general, sequence to sequence networks have a problem. Then that problem is the bottleneck layer here. It's that the intermediate states of the encoder portion of a sequence to sequence network are not visible to the decoder. And so the decoder has to come up with everything starting right there. Now an autoencoder does that, but because of this forgetting problem in a recurrent neural network, it's a little bit harder for a sequence-to-sequence model to do that. And this is why a newer mechanism called attention was invented. Attention is a way of exposing all of the previous states of such a recurrent neural network. So hidden state 1, which is forwarding to state 2, to 3, to 4. And each of these states is visible to each of the decoder states based on a mechanism called attention, which looks at the present decoder state and together with all the hidden states decides how much it wants to let through. This is achieved via softmax, where the sum of all of these is 1. So it gives you a weighted summation of the hidden states that's customized for each decoder state. This is really what attention is. And you see that the attention mechanism makes it so that the weights change in a neural network dynamically as the neural network operates. So this is different from learning the weights of a neural network, which are fixed after the training. When there's an attention mechanism, the current state of the neural network determines which previous states the network chooses to see. And this allows the decoder to adaptively choose inputs in order to make its decoding task a little easier. So in our sequential language translation task, if you're translating a verb, you might want to pay attention to the verb in the other language. And of course, verbs in languages like German are often at the end, but verbs in English are normally the second element of the sentence. So this decoder state might pay more attention to this encoder state, and so on. And this was actually a very drastic advance in the functionality of NLP tasks within neural networks. And it actually eventually led to the proposal of the transformer. Now the transformer is not really sequential in the sense that you have the same set of weights that are being reapplied over and over again. It's actually something like a convolutional neural network where you have all of the inputs available from previous states, and the attention just chooses which to look at depending on the place in the decoder sequence. And that's why the original paper on this was called Attention is All You Need. So this was a quick crash course on sequential models, the types of tasks they might do, and the ways they might be implemented. But you might be wondering, aren't some of these tasks actually supervised, like language translation? Wouldn't you have the answer to training? It turns out that these are similar to sort of autoencoders that are denoising or something like that. They have the same amount of information that they need to recreate back. so they could be used in a completely unsupervised fashion. So unsupervised training is frequently used in language models as either pre-training or for language generation. One way to train a network to generate whole text corpuses or whole movements in orchestral music is to train it to mask a part of the input and repredict it back. And so what this does is it teaches the neural network patterns that allow it to fill in the music so that it makes sense. So then you can feed it in a few notes and just ask it to complete, and then you've generated some music, and then you can feed that generated part in again and ask it to complete the sequence. And this is actually how a lot of commercially available music generators now work. And of course, this kind of mask training was also key to some of the very popular language models, such as GPT, the GPT series of models that was produced by OpenAI, where some of the language and text was so realistic that the creators felt that it might be too dangerous to release at some points. If you want to read more about this, here are some blogs that are fairly friendly.